Our microcontroller and embedded system topic, other system components. So here we will discuss the components like reset circuit, brown out protection circuit, uh, your RTC, real-time clock oscillator, also the watchdog timer. So literally these components are used as a protection circuit for your microcontroller or microprocessor. The reason why I call this as a protection circuit happens to be, think as if you are working in a desktop, your computer, and if you are using many applications, more than 5 to 6 application, you have a situation that your system may get hanged. So in that case, suppose if nothing works, then the last try what you gonna give would be you will press the reset button. Upon reset button, the system will reboot and everything will proceed normally. So if there is a situation that if the microcontroller doesn't behave in a normal manner, that is if it gets hanged up when it has been connected to different peripherals, then you have an alternative option like reset. By using this reset circuit, you can ensure that the microcontroller or processor behaves in a normal manner. So you might have observed this condition again while working with stepper motor interface program, part B experiment. So suppose if the stepper motor was rotating continuously, you don't have an issue. Now suppose if the question was posed like make stepper motor rotate in clockwise direction for 60 steps, so count 60 steps. So in that case, suppose if you go wrong while counting, then you can use reset button and again you can count the number of steps. So in that case, automatically again this system will rerun. So here what happens when you press a reset button, we know in ARM Cortex you have a vector table for exception and interrupts defined, and we know that the vector address 04 is for reset handler. So in that address you have the reset handler subroutine starting address. So directly when you are picking that word from the address 04, directly the jump takes to the reset handler subroutine, and the content present in that reset subroutine will be run, so which is literally used for rebooting your controller or processor. So here you have a basic circuit which may not be the circuit used in your Cortex M3 machine. So this is a simplest circuit used for resetting your microcontroller. This pin is connected to the reset line of your controller or processor. So over here this pin is connected to the controller. So here it says reset pulse active high. So literally initially this will be active low and it is pulled to active high when this VCC supply falls below certain voltage. Similarly over here, initially the pin will be high in the high position. Then when this goes bad, then this will be triggered to low position. So it is used for functioning your reset. So this will be used if pin accepts high signal. This will be used if pin accepts low signal. If reset pin takes active low, then you have to use this circuit. If the reset pin takes active high, then you have to use this circuit. So the working of this circuit, so you have a capacitor, resistor and a freewheeling diode which is connected in parallel to the resistor. So when VCC, assume VCC for literally microcontroller or microprocessor is 5 volt. So if 5 volt is given, constant 5 volt is given, you can think as if the controller is getting that voltage sufficiently. So in that case, since you have a capacitor over here, the capacitor is going to get charged and you will not be getting any voltage at this line. So this will be active low. Capacitor gets charged, we don't have any pulse here. So this pulse is active low pulse. So as soon as this voltage, VCC voltage, drops below certain range, or think as if there is a connection breakage, so you think as if there is a 0 volt or lower than 5 volt. So in that case, since you have already a voltage in this capacitor, so this capacitor discharges. So while it discharges, it follows this path. So you're gonna get, initially there was low signal. Now all of a sudden this will give you a high voltage. For a small duration you get a high voltage due to the capacitor's voltage. Capacitor is going to discharge the voltage whatever it is having for a small time, and that small time is defined by the values C and R. So if you want that time to be sufficiently large, then set the value of capacitor and resistor as required. So you get kind of a spike. So slowly it will decay, depends on RC value, but initially from low you get high signal, you get a high signal. 5 to slowly till towards 0 it goes low. So that's what happens, hence you call it as an active high, because for a short duration you get active high signal, that is the discharged voltage which will be obtained here at this terminals. Similarly, one more example you have. So here what you have is VCC and capacitors is over here, and you have resistors. So in this case, when voltage is given for a while, then the capacitor definitely gets charged up, and it will reach the voltage VCC. And at that moment, so at this point you get the voltage will be exactly equal to the capacitor voltage itself, approximately. So this will be in the active high state initially. So as you pull off this connection, as the voltage given to the microcontroller, if it's disturbed, if it's not running normally, then you can think as if the capacitor will discharge, and literally it will take this path. At that time, when you use a oscilloscope or a pointer to mark the voltage graphed over here, so it would be lower. So from high it goes to low, and that implies you have a active low signal, then it will remain very low. So ensure that the capacitor discharges quickly in this case, so you get low pulse for a while. Then all of a sudden, if you get a proper voltage, then you get high voltage. So active high will continue. So when you have active low state for a while, at that time this connection has to be given to the microcontroller to reset. So understand when you are going to reset the sequence. So when the signal is active low here for a small duration based on RC, you're gonna reset the sequence. At this condition, it is for a short amount of time, it will be active high. In that case, you have to reset the sequence. Okay, so second circuit which we will discuss, that is brown out protection circuit. This again is a circuit used for providing the reset pulse to reset your microcontroller. This again is an external circuit. So this circuit consists of a transistor, a diode, Zener diode, and yeah, two things you will be using. So the way this works is, so you have a VCC voltage, and you call this voltage across base to emitter as VBE, and voltage across Zener we call it as VZ. Now we can call that the transistor will be turned on. It will be in on state. It will be on state when VCC voltage, when this voltage is greater than the sum of the voltage between VBE and VZ. So if VCC is greater than VBE plus VZ, then you are going to this transistor will be in on position. Suppose if the voltage, sum of the voltage VBE plus VZ is greater than VCC, then the transistor will be in off state. So here, how do you determine when this pulse has to be activated? So this pulse has to be activated when this voltage, that is Zener voltage which we have. So in the Zener voltage we will provide the threshold. We will provide the threshold to the Zener voltage. So if this voltage is higher than this threshold voltage, because this is very small voltage. If this is higher than this voltage, then this will be turned on. Suppose if this voltage falls below this predefined threshold voltage, when I say when this falls below the threshold voltage, it implies that this has a problem to deal with. So the voltage is not fair enough, which you have given it to the microcontroller. So in that case, this will be turned off. So when this transistor is turned off, you get a active low signal, and it is connected to the reset pin which receives active low signal. So when it gets a active low signal, this controller will reset the system, or it will reboot the system. So just remember, the condition which you require is this VZ, the voltage across the Zener diode. In this you will store the predefined threshold with which you will be comparing it with VCC, and if this predefined threshold voltage is greater than VCC, then you are going to get an active low signal. If not, it will turn on this transistor, and you'll get active high pulse here always. So active high pulse, this will not work. Active low pulse, it works. So this is about brownout protection circuit. The next topic which we'll be discussing is the oscillators. So oscillators, we require oscillator. Oscillator provides the frequency for your microcontroller or microprocessor. So what is this? Why is this required? Suppose if you want to run an instruction quickly, then definitely we expect the clock frequency of that particular device to be very much higher. But there is a problem when we try to increase the clock frequency of a particular machine, like a microcontroller or a microprocessor. You require more power. But we had already discussed the main advantage or main application of your Cortex machine is to design it is for those application where the power is lesser and the performance is greater. But there is always a trade-off. So if you want a very good performance, then the clock frequency should be higher, but it will also create a problem. The power required will also be higher. So here the oscillator frequency, you have two ways for your microcontroller. One could be generated. You can use an oscillator unit with two wires, and you can use a resonator circuit, which you call it as a crystal resonator circuit. This will be used. So this resonator circuit, parallel to this you have two capacitor. So these two are used to tune the frequency. If you want to vary the frequency of the circuit, then you can use this capacitor, and this resonator circuit will create the frequency, and this is connected to the oscillator. So this is something like the oscillator unit which you have is just having two wires, and frequency is generated using this resonator, and you'll be giving it. So you call this as a quartz resonator circuit, whereas in oscillator circuit, this whole frequency generation, frequency provided for your microprocessor or controller is provided by this unit. So this is a standalone unit which provides the clock pulse. So this is the difference between oscillator, crystal oscillator. Crystal oscillator is the second one, and this is your quartz crystal resonator. Crystal resonator is used mainly to generate the frequency, and that frequency is in turn given as a input to the oscillator unit. Over here, this itself is going to produce the frequency what you desire. Okay, so some controllers comes with built-in oscillator frequency. Some you have to provide a external frequency. Okay, external oscillators are required some cases, some scenarios. In the computer itself, a frequency will be there. So this is about your oscillator unit. The next one is your real-time clock. So real-time clock, why it is required and what it will consist, we will discuss. Now suppose think as if you have a computer at your home, and we will turn off that computer, and after a month I'll open the program, or I'll restart the program, or I'll power on the system. So if I do so, the time which you will be getting it on displayed on the screen, it will show you the exact time. You may think there is no internet, we have not connected it to the internet, but still, how come after 30 days you are going to get the exact time? So all this is due to the unit, what you call it as a RTC, which is a real-time clock unit, which is connected, which is interfaced to your system. And this real-time clock unit requires a very low power, and it will run for years without any issues. And this RTC is also having a battery backup, a small, since it can work with small power, a small battery is provided to this, and literally it will give you the time, hours, minutes, seconds, even the date, month, year, all those information. If you require, you will get it. For example, you can consider a digital watch. Analog watch never had all those features, whereas the digital watch which you are gonna get now has all those information, even the date, time, the hours, seconds, format, everything will be looked on the screen itself. Everything is available in the screen. So there you have probably a RTC unit with more features. A similar type of a feature, the RTC, is also involved in your desktop machine. So suppose if you might think how the operating system is gonna get that RTC information. So RTC information, when you install the operating system definitely will grab those information from the RTC module. So it gets directly, even if you connect it to the internet without connecting it to the internet, even though you will get the exact time from the RTC. So RTC is the one unit which is going to provide you the correct timing based on the hours, seconds and time form. Okay, so this is bit theory. So RTC we have discussed, and the last topic of this module is Watchdog Timer. So hope you are aware with the word firmware. What is firmware? Firmware happens to be the software which the manufacturers who designs the product will burn that program in it, and it will be dumped into the program memory, and you at any cost cannot modify it, destroy it, and it is used for booting the system in some cases. And also you might have heard about ESP8266 module. When you purchase that online, then initially there will not be a firmware dumped into it. So what you have to do is you have to search the relevant firmware for your hardware. The hardware specification will be given, and once you know that specification, you can search for the firmware. Then you can even dump the firmware. Once you dump the firmware, then you can interface this ESP8266 module with your microcontroller like Arduino for communication purpose. So firmware essentially will have the boot program to run the machine to enable your system, that is ESP8266. If you want to start that IC, then firmware is required, that is booting your IC. Then along with that, firmware will also include the baud rates which are essential for transferring a data from your Wi-Fi to a microcontroller. So all those information relevant is essential. So all will be there, and it will be there sometimes, some occasion firmware will be dumped onto the IC. In some situation firmware will not be there. Okay, and so here how this firmware, why Watchdog Timer you are using. And this is used in case when you execute a firmware, that is when you run your application, booting application. Suppose if things goes bad, if there is a situation like due to multitasking, if the firmware execution doesn't work properly, if it's not working according to the way it should be, then you can always introduce a hardware timer, which you call it as a watchdog timer. So this watchdog timer will be connected to the reset pin. So if there is a situation that if the firmware execution doesn't work normally, after a while, after some 10 or 15 seconds, still if firmware execution takes place, it is not something like it is executing normally. So it has been broken or it has been hanged. In that case, you can produce a signal from the watchdog timer, and it can be given to the microcontroller, and the firmware execution program can be rerun again, so that the properly the microcontroller will handle this application. Okay, so you can just figure out what basically happens. This is the block diagram of the watchdog timer unit you have, and you have a controller, and assume that the firmware is actually the first program which will be run on this machine. So when the firmware is running normally, you don't have any problem. Then what happens is you have a timer set in this watchdog unit. You can think as if it is wait for 20 seconds, something a count you have to use, and that count will be loaded in this watchdog timer register. Okay, the count after which you have to produce a reset signal to the reset pin of the microcontroller. That will be stored in the watchdog timer register. So once you get a signal, if this is working normally, then what happens is within that stipulated time which is addressed here, so if you're getting a signal back to the watchdog timer, it means your firmware execution is working properly. So if you're getting a signal back to the watchdog timer within the time which you have specified in the watchdog register, then it means the firmware is running properly. Suppose if there is a problem, if it gets hanged up, then you wait for a while. After 20 seconds, even if this doesn't execute the whole application, then there is a problem to deal with. So in that case, the counter, once it reaches 20 seconds, then it provides a reset signal to the reset pin of this microprocessor, and the firmware execution application which has been stuck in between will be rerun. So that's what happens here, and here you have to know when to enable the watchdog timer. So it will be enabled by writing a 0 to this unit. To this unit you have to write 0 before executing the firmware program. Before executing the firmware program, you have to write a value onto this unit, or there are a couple of registers associated with the watchdog timer. So those registers should be made use to enable the watchdog timer to introduce a value into the watchdog register. That is actually the time after which you have to pass a signal to the microprocessor to reset the microprocessor. Suppose if the computer is hanged due to the firmware issues. Fine, that's what we have. Next module 4 we will continue with. This is the end.